Distance Education. This is MBF3C, grade 11 college prep math. I'm Pete and I'm your teacher. So today's class is pre-recorded, so don't call in. I'm traveling up north today, so if you're seeing this, it means that I'm traveling, and so the class is coming at you through the pre-recording system. Okay, and we'll be back tomorrow with the regular class. So if you do have any questions, just save them till tomorrow's class, and we'll be back live. Okay, so what I'm going to do here, we're going to do lesson 15, which is about creating nets, but I just want to wrap up lesson 14. Okay, so if you were watching yesterday's class, we would have gone through the different problems and the different approaches to problem solving that we have in lesson 14. The idea is to look at what you have, look at what information you have, what you need to figure out, and then pick the best tool to use, right, to solve the problem. Right, we're going to go through that 4-step problem solving model. First step, understand the problem. Second step, devise a strategy, which a lot of times will involve making a diagram and sort of writing on that diagram the things you know, and then figuring out what formula you're going to use, which technique. Now, sometimes, your choice of formula could be just as simple as which one you prefer to use. Right? It doesn't have to be really complicated. You can just use whichever one appeals to you, right? So, someone says, well, I can solve this with the law of sines. Yeah, maybe, but if you can use the law of cosines and you want to, nothing's stopping you. I'm certainly not going to mark you wrong if you use an approach that ends up with the right answer. So now it's hard to know how many of these I got through yesterday because I'm pre-recording this. So if we didn't get through all of them yesterday, then just expect that we'll come back tomorrow when it's live, and I'll just fix up any gaps here. But what I'm going to do is just talk about the last one in the key questions. Key question is on page 36, and it's key question 4. And the reason I want to talk about this one is that, again, this is one of those questions where having a diagram and understanding the situation is critical. Okay. I sort of joke that you need to know a little bit about baseball and golf and building construction, stuff like that. But it's by doing all these different problems, this is how you learn stuff, right? About different topics. And if you don't have all the information, how to figure it out, how to find it. So for question 4, it says a baseball diamond is a square. So now we know that the angles are 90 degrees with sides 27.4 meters. All right, well, let's draw that one out. I'll just use blue here. Now, remember that we can make our initial diagram, and we can always revise that diagram, right? There's nothing really to stop us. Now, we know that these are going to be 90-degree angles. I don't know if we need to know that, but it is useful. And then it sides 27.4 meters, 27.4 meters, and that's each one. Okay, so we'll just designate it that way. Now, the pitcher's mound is 18.4 meters from home plate on the line joining home plate and second base. So what they're describing then, okay, assume that that's straight, and then the pitcher's mound is 18.4 meters. So I don't know. There's the pitcher's mound, and that is, I'll just use a different color here. That's 18.4 meters. 18.4 meters. Okay, and that's from there to there. Okay, how far is the pitcher's mound from first base? So, this is first, second, third, and this is home plate. So what they're asking us in is how far is this place here from there? There we go. So there's the, okay. So now we have the geometry. Okay. We know that this angle here is 27.4 meters, and so we have two sides. We need at least one angle here to be able to figure this one out. Okay, I think. Or can we do it without knowing it? Okay, let's take a look. I'm going to redraw just the part where this is the pitcher's mound. Okay, this is first base. This is what we're trying to find. Okay, we know that that part. Okay, let's see what we can do here. We know that this is 27.4 meters. This is home plate. This is first base over here. And we know that this is 18.4 meters. Okay. So what do you say? We don't have enough right there to work it out. We don't have any 90-degree angles. We know for sure. We can't say that the angle between we can't say that angle right there is 90 degrees. I doubt it is. Just the way I've drawn it, it could be a little further into the square or a little closer to home plate. But we could make an assumption about this angle right here, because we know that's a 90-degree angle, and we know that this line goes on the diagonal of the square, so that line bisects the 90-degree angle. Okay, and so when you bisect the 90-degree angle divided by 2, we can safely say that is a 45-degree angle right there. Okay. All right. Well, which formula are you going to use now to solve that? See, so what we've done here for question 4 is we've taken it from a pile of words, and now we turn it into a diagram. Not just one diagram, but 2 diagrams. And this represents going through the 4-step problem-solving model, and we've gone through basically the first 2 steps. There's one little bit left at the second step, which is to write down which formula you're going to use, which approach. Now, you can't use Sohcahtoa because there's no 90-degree angles in there. So you're pretty well stuck with either the sine law or the cosine law. Okay, and I think if you look at that problem, you should be able to figure out which one to use. I think either of them would work. Okay, and so, but this is how you approach the problem solving in mathematics. You draw your diagram, it becomes messy. You draw another diagram that represents a clearer understanding of it. Draw a third diagram if necessary. Consult with someone if you need, like if you need to know, what a baseball diamond looks like. You use Google or just ask someone, So there's all sorts of ways to gather information and get through that first step, understanding the problem, and the second step, which is devising a strategy for solving it, right? As you could probably figure out, step 3 is implementing your solution, which is just a matter of sticking the variables in the equation and typing them out on your calculator. For the types of problems that we solve, that's not really a big thing. Right? But for when you get out in the field, that might actually be when you're working, that might actually be the bulk of your job. Where if you're in a veterinary clinic and you're being asked to calculate things, chances are they've already given you the process, right? So it'll be maybe just a little bit different. Okay. All right, so that was question 4. Hopefully we looked at the other ones in a bit of detail yesterday, but because this class is pre-recorded, I can't say for sure. If there are any gaps, we'll just come back and take a look at it tomorrow when the class is live. All right, well, let's take a look then at lesson 15. This is going to be a relatively short lesson because it's on a topic that's just a little bit off of what we've been doing. It's called creating nets, and it's actually a fun activity. They don't give you very much in the unit, and what I suggest you do is go on the internet and search for nets of solid objects. You can find all sorts of nets there, and if you're interested in it, I'm pretty sure I have some links somewhere So, just wait till tomorrow's class or send me a Facebook message and I'll put some links. Basically, um, if you print the net, you can cut it out with a pair of scissors, glue it all together, and you can make a three-dimensional shape. Now, squares are fine. You can make pyramids, different types of pyramids. But you can make some pretty interesting shapes out of nets. You can make um, uh, dodecahedrons, right? So 12-sided shapes. You can make octagons, 8-sided shapes. I've even seen some nets um, for 20-sided shapes, right? So yeah, it's you get some pretty big nets there. Lots and lots of folding to do. Okay, so what a net is a way of viewing a three-dimensional object when it's cut in such a way that you unfold it flat into one piece. Okay, so they're going to show an example of a box here that turns into a cube. But if you do any recycling at all, you're probably familiar with this because every time you recycle a cereal box, you're basically turning that rectangular prism into a net by unfolding it, and it folds out and flat into one piece. And that's what this is all about. It's amazing what sort of packaging can be made in just one piece. And nowadays, with everybody really conscious about the impact that waste has, how they all they do is glue it. They don't use staples anymore. They try to not use too many pieces. Sometimes, usually, it's just one piece, and so it's a kind of an interesting thing. So once you're aware of this, and you start looking at, for example, your Tetley tea box, when you start tearing that apart, or a pizza box, or just a regular cereal box, it's kind of interesting what it all turns into. Okay. Now, the nets are not necessarily one thing that if you're there's not just one net for a box, right? You can have um, different nets. For example, um, example, if they don't have a number, this is on page 38. So they show one net for a box. So you can sort of see that you kind of fold this flap up, and then you fold that flap over, and that flap over, and then you'd fold these two over, and you'd end up with a box with a lid. But if I were to draw that net this way, okay, let's see, do I have enough? Oh, I need one more. Yeah. All right. I'm gonna fix that. I thought I was doing so well there too. Okay. So that's one, two, right, and then one more. All right. So something like that. I imagine that those are squares, right? So we could then fold these ones up. So those would be the sides, and then these three segments would kind of wrap around, right? And it would actually this part here would end up being kind of the wall, the back wall of the box, and then this would be the lid, and then this would be the front of the box, right? So there's more than one way to make a net, for a lot of shapes, right? So, and it's just it can be a fun activity, and if you have kids, they like doing stuff like this. Okay? It's sort of seeing how a flat piece of paper, you cut it out, and then it turns into a three-dimensional shape. So you can make all of the different shapes. You can make a square. You can make a a tetrahedron, it looks like a triangle, but it's got four sides, right? You can make different types of pyramids, cones, even all sorts of things. Now, I will warn you that some of these might be a little problematic, some of these shapes. I think the key questions are a little problematic, so we're going to go through them because it's a really short unit, and really I'm just looking, when I'm marking your key question for this, because it's such a short key question, I'm just looking for your engagement with the material, not necessarily Yeah, because there's really not a lot of work to do in this unit. So it says below, this is support questions, this is page 38. Below are examples of nets. So the net is the flat um, the flat representation of three-dimensional shape with lines showing you where to fold or cut. Okay. So which will produce closed objects? Explain why others will not. Okay, so that's really the kind of the point that we want you to kind of look at it and say, well, you know, sort of say, no, this can't be, right? That's what we're trying to go for here. Now, if you think about this E right here, if you fold that flap up and you fold that flap up, right? You have two triangles, right? And then if this is folded up, then this will join with that. And if this one's folded up, then this will join with that. Now, there's nothing to stop you from tracing or photocopying the course material and just actually cutting that out. And in fact, if you wanted to try that, I would suggest you put it on the photocopier on 2x to double size it, make it a little easier. But you could try it out, and you would find that that makes a triangular prism, which is basically, let's see if I can draw one of these real quick here. Yeah, something like that. Uh, you may have seen candy bars that are there you go. That's how it looks, kind of like that. You may have seen candy bars that are in that type of triangular box, Toblerone bars. I don't know. Those are the ones that everyone seems to like. That are in that triangular box. Okay, so, but you could actually now, if you understand nets, then let's say that you wanted to give someone a present. Let's say you want to give them a rolling pin, right? And you give them a rolling pin, but instead of wrapping it up in paper and then they know it's a rolling pin, right? You could make yourself a triangular box out of some cardboard, right? Make a triangular box. It's big enough to fit the rolling pin. Put the rolling pin in there and then wrap it. And then they'd be stumped. They wouldn't know what it was, right? So there's something to be said about knowing a little bit about that geometry. Now, the point behind this is really just to get you thinking about shapes and how the flat version of the shape relates to the three-dimensional version of the shape. Now let's take a look at D. This looks kind of crazy. This is a rectangle with two ears sticking on it, right? So what we want to do is think about, what does that look like? What would that look like if I tried to turn it into a shape? Okay. And well, if I folded that up 90 degrees and then folded that up 90 degrees, okay, and then, so what I would have is basically a disc here and a disc here, and then I'd have this kind of this sheet off to the side, right? And if I wound that sheet around the side of it, yes, indeed. So what we would have then, look at that, is a cylinder, right? So this is the sheet that you would wind around. Okay. Now, if you'd sort of have to decide if you have enough to go all the way around the circumference of the circle, but we're not getting into that level of detail. We're sort of assuming that it'll work. Okay. All right. So that's what you have. It's a cylinder, right? Now, how about B here, right? What is B? What does it look like? Well, you can imagine if I fold that flap up and that flap up, those could be ends of a box. And then the question is, do I have enough stuff to actually make an entire box? How many rectangular sides does a box have? Like a butter box or something, right? You could actually take a butter box if you get your butter in a box and open it up and take a look at it. Okay. So as it turns out, indeed, you have four sides, right? You have the front and the back and the top and the bottom. So when you fold that up, that turns into a box, a rectangular box. Now, if you were to go onto the net and look for a net for a rectangle, what you'd probably find is a lot of them have these little tabs on them, right? And those little tabs are there when you're cutting them out. You're supposed to put glue on that tab or tape or something so that it makes it stick together a little better, right? Otherwise, you end up having to tape the edges of things, like right edge to edge, and it's kind of hard to do, and it's hard for kids to do that too. With their motor skills are not quite uh, as as good as adults. So that's when you print those off on the net. When you print nets off on the net, they have little tabs. A lot of them, the better ones have tabs. Okay. All right. Well, let's try something like C. What does that look like? I'm just going to scroll down a bit, and what I'm going to do, I'm going to extend the page so it'll pop up. Sorry about that. If I think about C, and I think about this being the base of something, okay, and then I just kind of bend that up and then kind of curl it around, right? What we end up with is a cone. Okay, I don't know if I drew that really well, but yeah, we end up with a cone. Okay, an upside down cone from maybe what you're used to thinking about, like an ice cream cone or something, or a coffee filter, something like that, right? So that's what that looks like. Now, what is this thing? Okay, well, it's got a square base, so it's going to be a square base something or other. There are a lot of pyramids that have, like, they're called after the base of the figure. So if it's got a square base, called a square base pyramid. If it has a triangular base, it's called a, well, triangular pyramid, which is also a tetrahedron. A pentagonal pyramid, all sorts of different pyramids. But anyway, yeah, if you were to bend these up until the tips touched, then you would end up with, yeah, with a kind of a pyramid, right? That's what it would look like, right? Like that. Something like that anyway. Okay, so you can try that. So the answer here is that for this question is that they all produce closed objects, right? And you say why or why not? Well, I think explaining it in words that, naming the shape of the object or describing the shape of the object would be sufficient to answer the explain why part. You know, if I'm calling this a cone, right? Or if I'm calling this a square-based pyramid, if you're just telling me it's a, four-sided figure, five-sided figure, um, it's fine, right? Closed figure. All right, and then we jump right into the key questions here. Okay, and I just want to point out a little bit about the key questions that there's some problematic parts of this. Um, For each of the nets given below, draw another net that will produce the same object. Okay, well that's fine. The problem with this first one, A, is that this part here is superfluous. That part really is wrong. I don't know how that ended up on there. So now what we have is a figure where if you put bend that one up, right, and bend that one up, and then you can kind of rotate this strip around the center. You're gonna have something that looks a little bit like a tuna can, right? That's what it looks like. So then the question is, well, what could you do? Like, how could you change that, right? And so and I'll straight up show you what it's gonna look like. Um, the way you change that is um, recognize that the strip, it doesn't matter where the ends are. So you put the end here and here, right? And it produces the same thing, right? It gives you the same result. Or you could put one end down at the end of the can, down on one side of the strip, and then you could put the whoops, you put the other end up there. It won't really change anything. Okay. So there you go. I think if you put them on both sides of the strip, though, it wouldn't work because it would have two ends on the same side and then no lid. Okay, so that's what they're asking you to do here, is to try and imagine what this would look like, and then come up with an alternate. Right? This is a box with a lid. So the question is, does that flap have to be there, or could it be there? Could this flap be right here? Could you just have it like? Could you just have this one flap here, and then that flap, and that could that still work? Right? Could this part you know, let's see, I don't really know. Yeah, so just try different things and see how it comes out. Okay, so like I say, this is not a this should not really be a humongous issue here, right? So if you can identify these like that, that's a triangular prism. So if you were to go on the internet and Google net for triangular prism, you could probably find something. This is a rectangular prism, and that's a cone. Okay, so you've already seen what these look like anyway. Um, but for example, C, there's really not a lot to do with that. It's kind of, it looks a lot like, oops, like this one back here. I don't know that there's really a second way to do that. Where are we? C, this one right here. That's what it looks like. Okay. The only thing would be where that circle, where the bottom it goes. Okay. Otherwise, you're pretty well, right? It's going to be like that, and then going to be something like that. Right? There's no real variation. Okay. And then identify patterns that will produce a closed three-dimensional object when folded. Explain your reasoning. So again, what we're really trying to say here is, for example, D, you know, it's a box with a lid. We've got 1, 2, 3, 4. So we got the 4 sides that would wrap around, and then we got the 2 ends. So we have all 6 sides that we would need to make, and it's a small little box. It looks something like this. Okay. Yeah, so it looks something like that, right? So you could even say, all right, well, this is going to be 1 here. So that's 1. This is going to be 2. Oops, that's going to be 2. That's 2, right? And then 3, we can't see it. It's in the back. And 4, we can't see it. And then that'll be 5 and 6, and that would be 5. And we don't see 6. So anyway, you get the idea, right? Uh, So, and you could try, okay, so how about something like this, right? If you were to fold this flap up and that flap up, the thing is that they don't form a point, right? These two flaps would overlap each other. Okay, so they wouldn't really work, right? They would, and there'd be a gap, probably be a gap right here somewhere when you folded it up. Okay, so again, we're kind of trying to kind of looking to have a bit of an explanation for why it'll either work or not. Okay. All right. And you know what? That's it. So it's a very, very short key question. And this is why I went through them. I think there's only 3 questions there. Make sure you make this correction here. Otherwise, it's going to be a little bit confusing. Okay. So that's unit 3, and I'm going to do a bit of a review now, and we'll spend a few more minutes on unit 3. For tomorrow's class, make sure you bring unit 4. Okay, unit 4 is going to be, well, we're going to change over to do some data management and things like that, some probability. So be kind of interesting surveys, things like that. So just a little bit of an interesting end. And again, in in Unit 4, most of the key questions are really short. There's one that has a little bit tedious. It's a fairly long key question, but I'll even show you how to do some of that on Excel if you want to kind of speed things up a little bit, or at least learn another skill. So that'll be Unit 4. But now what I'll do, because we have a few minutes left, I'm just going to go back and just do a little bit of a review of Unit 3. Okay, so Unit 3 was all about geometry, trigonometry, mostly the study of triangles. The last little bit was just kind of an add-on with the nets. Okay, so let's just go back here, and okay, we'll just go all the way back. So the first bit, and probably some of the most important bit, is the geometry of triangles, the nomenclature, the words that we use to describe triangles. Okay, where a right triangle is going to be a 90-degree triangle, and that the triangle, all right angle triangles, right triangles, have a hypotenuse and two legs. Okay, that's how they're called. Okay. The other thing that's important, and this applies to all triangles, that the sum of the interior angles of the triangle are 180 degrees, and that's all triangles, not just right triangles. So if you have two angles inside a triangle, you can figure out the third one just by subtracting the two that you know from 180 degrees. Okay. Now, the, another key for um, the study of triangles is SOHCAHTOA. 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 If you can commit that to memory, you will have a big help when it comes to solving right angle triangles. SOHCAHTOA, because then you will always get the trig ratios correct, the sine, the cos, and the tan. Okay, so SOHCAHTOA. Now you have your calculator with you, right? And you see the sine, the cos, and the tan. And SOHCAHTOA comes from sine, cos, and tan. The other thing you'll notice is that the H is repeated in the first two syllables of SOHCAHTOA. The H, the hypotenuse, is the longest side of the triangle. So when you're working out a sine ratio or a cos ratio, that means that the number that you work out that ratio should be less than 1, because the hypotenuse, which is the denominator of the ratio, the fraction ratio, should be bigger than the numerator. It has to be. The hypotenuse is the longest angle. The only time that that might change is when you're doing tan, because tan, it can be either above 1 or it can be below 1. That's the only one that's a little bit different. Okay, so when you're working out sines and coses, the number is always going to be positive and it's always going to be less than 1. Okay. All right, SOHCAHTOA. Now, the other thing to understand is that when we're looking at right triangles, the right triangle always has a right angle symbol at the 90-degree side, and then the side opposite, the one that doesn't touch that 90-degree angle, is called the hypotenuse. Okay, and it never changes. There is only one hypotenuse. It's always in the same place. It's always the longest side of the triangle, the right triangle, and it's always complete. It's always opposite the right angle. Okay, so now that you've been through the whole unit, maybe this makes a bit more sense to you, that the hypotenuse doesn't touch the right angle. Okay, it's on the other side of the triangle. Now, in terms of the opposite and adjacent, that changes depending on the angle we're considering. The hypotenuse always stays the same, but the side opposite an angle, say A, is the side that doesn't touch that angle. Okay, and the adjacent is the other side other than the hypotenuse that touches the angle. So hopefully you'll be consistent in identifying the opposites and adjacents. Now when it comes time to look at a different angle in the triangle, such as B here, the hypotenuse stays the same, but now the opposite will change. I'm going to change that to black. The opposite now becomes the side opposite the angle that you're considering. And it actually flips around, if you notice that. For A, the opposite and adjacent are reversed when you look at B. Okay, when you switch to B, the opposite and adjacent change. So that's something that when you're working through your triangles, when you're working through your trigonometry questions, keep that in mind as you switch from one angle to another. Hypotenuse stays, but you really need to scratch out the opposite and adjacent that you've written down and rewrite them for the new angle that you're considering. Okay. So the sine ratio, and like the cos ratio and tangent ratio, is just a ratio. It's just a number. It's one of the few unitless numbers. It's not a unit of measure. It's just a number that we have. But when we have that sine ratio, we can use the inverse sine function to look up the angle that corresponds to that ratio. Okay, and that's what makes this very powerful. Now, if you went to school a while ago, we used to look up those numbers in the back of the textbook. That's why our math textbooks were so thick, because they had all these tables. And one of the tables was the trig ratios, and it usually had 3 columns: sine, cosine, tan, and then you'd have, you'd be able to look it up as your, um, whichever ratio you had, whichever angle you were trying to get. Okay. Now we did talk about putting your calculator into DRG mode, into degrees mode, by pressing the DRG button. Hopefully you have that sorted out by now. And again, if you had some problems with it, or if maybe you get a new calculator, feel free to just send me a picture of your calculator, and I'd be happy to help you. Or if you're using an app, an iPhone app, just tell me what the name of the app is. The built-in calculator works fine. I use an app called pCalc of mine. I think I paid a couple of dollars for it. pCalc. And the reason I use that one is that it functions the same way as a calculator that I kind of used quite a bit back before I was a teacher. When I was an engineer, I used, there's some calculators that we really like, and that were quite popular amongst engineers, so just use it, pCalc. All right, let's see. So we have the sine ratio, and we work through all of those. And the sine ratio works then when you have, when you need an angle and you have a hypotenuse in the opposite side, or if you have an angle and a hypotenuse and you need the opposite side, right, or you need the hypotenuse, right? So that's where the sine ratio works. So one of the things that you're going to see then in the problems that you do maybe on a final exam, and it's certainly the problems you've been doing in Unit 3, yeah, Unit Lesson 14, is that they don't tell you which one to use. So it's up to you to kind of look at the situation and pick the one that's appropriate. Okay. All right. So the next thing that we did then was we looked at the cosine ratio, and that's really the same thing as the sine. It's just that instead of opposite over hypotenuse, we're using adjacent over hypotenuse. Otherwise, it's the same. And what that does is it opens the door a little wider to figuring out things about triangles when we don't have necessarily this, like if we need a side or we don't need the opposite, we need to figure out what the adjacent side is. We have an angle and a hypotenuse, and we can work out what that adjacent side is. Or if we have an adjacent side and an angle, we can work out what the hypotenuse is, right? So it just gives us one more tool in our toolkit, and that's really all it is. Okay. Of course, we're using the inverse trig functions to find when we have the ratio and we need the angle. Now, the last one that we looked at is the kind of the oddball of the set, but it's very, very useful, and that's the tangent ratio. Now, one thing I want to point out, if you haven't done it already, on page 12 of your textbook, there's a mistake in the diagram. Somebody just cut and pasted the wrong diagram here. The diagram that we really want is to show that the tangent ratio is the OA TOA in socket TOA. It's the opposite over adjacent. Okay, so it's basically, if you look at the first two of them, right, sine and cos, sine is opposite over hypotenuse, cos is adjacent over hypotenuse, and so then tangent is opposite over adjacent, so it's the first two, it's the numerators of the first two trig ratios, opposite over adjacent. And that helps us when we don't have a hypotenuse, which very often that's what we're trying to find, is the length of some hypotenuse when we have a situation where there's a right angle. Okay, so a lot of times we'll have that. Or, we could have a hypotenuse and an adjacent, or a hypotenuse and sorry, what, let me just walk back a little bit here. So the tangent is when we have an opposite and an adjacent, we need an angle, or we have an angle and we have an opposite and we need an adjacent. We don't need the hypotenuse. Sorry about that. Okay, but once we have the opposite and the adjacent on a right triangle, remember that the hypotenuse is a matter of plugging in the opposite and adjacent to find in the Pythagorean theorem. So don't forget about using the Pythagorean theorem when you're working with right triangles. Okay, the Pythagorean theorem can get you the hypotenuse. The Pythagorean theorem can get you either of the sides if you have the other one. Okay, so you don't even need an angle to get sides. Okay, with the Pythagorean theorem. Okay, so that may be a sort of a way if you need an angle and you know you need a side as well, you might actually be able to get some traction by applying the Pythagorean theorem to get a missing side, and then that'll open the door to getting you the missing angle. Okay, so you know in a way these are like solving puzzles, right? Jigsaw puzzles or something like that, where you have a certain amount of information, you kind of got to look at it and decide, you know, how you're going to proceed. Okay. Now, for the key questions in lesson 11 were kind of, they tended to not be too challenging as far as which um, formula you use. You know, it was pretty clear which one they wanted you to use for most of them. But later on in in lesson 14, that's when things get a little bit, you know, they don't tell you exactly which one to use. Okay, so there you go. So key question 11. So go ahead and hand those in. Now, if you're not sure, you know, you want me to informally look at it, it's fine. You can just send it to me. You can fax it to me. Just put a little note on it saying, please look at this or something. I'll be happy to do this. Your marks aren't cast in stone. If you send something in, even if it's for marking and you're not happy with your mark, just redo the part you're not happy with, send it back in, I'll change your mark. Okay, so that I want to make that clear. Okay, it's a philosophy of education that means um, that we're recognizing how much you learned, right? Not whether you learned it the first time, but just ultimately how much you learn, and that's important, right? You know, that's exactly what you want. Okay, if you get someone to fix your car, right? So you don't really care whether they fix it in the first hour or two. What counts is that they fixed your car, right? Well, I think they might charge you a little extra, but you get the idea. Okay, so the next thing we looked at after we finished our study of right triangles in SOHCAHTOA, then we asked ourselves the question, but what if there's no right angle? Right? What if we don't have a right angle? So a lot of geometry problems end up with a triangle, and you can't assume that there's a right angle. Now, it is possible, very often, quite possible to kind of split the triangle into pieces, and sometimes you can do that. You can drop a perpendicular down, and then you split it into two right angles. But that has its own issues doing it that way. Oops, I just really made a big mess of that. So, you know, it's better just to, if possible, to just try and apply one of the two laws. Now, the sine law, pretty straightforward. It's just ratios of the sine um, with the opposite sides, right? So the sine of a particular angle divided by the length of the side opposite is equal to, and that the sine of the other angles divided by the length of their opposites. Okay, and it's just a fundamental law of triangles, the same as that the interior angles all sum to 180 degrees. So you can use those ideas then to solve a quite a large class of problems where triangles show up. Okay, so many problems can be solved with the law of sines, especially if you can't solve it with the law of, with SOHCAHTOA, right? Okay, so and I think we went through all these questions pretty well here. So now the next thing then that we looked at was this, and that is the cosine. Oops, the law of cosine. The law of cosines is really for those cases that just can't be solved with the law of sines. Okay, that's the kryptonite of the geometry, the trigonometry world. Okay, because you bring that out when other things haven't worked. Okay, um, so one of the more powerful things is that it can, if we know two sides and we have an angle, we can find the missing side. That really is very powerful. Okay. If we know three sides, we can find any angle, any one angle in a triangle. And then once we've done that, now we've got things going, because once we have one angle, then the law of sines comes back into play, right? So that's why I call it the kryptonite, because really, as long as you have a little wee bit of information about that triangle, you're going to be able to crush it and get everything out of it um, with the law of cosines. Okay. Now the text shows you the law of cosines. It shows you all these different variants. I suggest you learn how to write it out using the pattern, which is that the side you're looking for is equal, the square of the side you're looking for is equal to the square of the other two sides minus 2 times the length of the other two times sine times the cosine of the angle opposite the side you're looking for. If you learn it that way, you're not going to be having to come up with all the different variants. Okay, write it down and then go back and check in the book or something like that. That's what I suggest anyway. Okay, now so that was using it to find a side. Now every once in a while you're going to have to use it to find an angle. Then things get a little more complicated because you have to change the um, arrangement of the formula. So I went through the way to derive this. Might be useful for you to do that. I see I made a little mistake here. And that's the thing, right? It's the pattern. It's the B and the C, right? And that's what we're looking for, is the B and the C. I don't know how I got off on the wrong foot there, but anyway, but you'll see that once you get used to that pattern, it's very straightforward. And then the other thing is that in the text, they kind of rearrange things so that you don't have a leading negative sign in your numerator, which I think makes sense. It just, I don't know, just I might not bother doing rearranging it, but I did just because that's the way they do it in the book. Okay, so then we end up with this nice little, well, I have it right up here in red. We end up with this nice little formula. Okay, which you could try, you just commit that to memory if you want. Okay, knowing how to derive it will make it a little bit safer in case you forget stuff. Okay, so once we have that formula, then it's pretty straightforward. Just plug in everything we know about the triangle, which is basically all the lengths of all the three sides. That's what we need, is the three sides. And then the angle that we're finding is the one side that it's the side that we plug in right there. Okay, and it's the side that we don't plug in anywhere else. Okay, so it will only appear once. Okay. Okay, and that was pretty much it. And then the next thing that we did was the questions, where lesson 14, and this was just pure strategies for trigonometry. Okay, so we looked at this, and we were really applying the the four-step problem solving process, right? We really have to use that, understand the problem, which usually means a diagram, some numbers on your diagram, maybe even a second diagram, and then a step 2, which is to develop a strategy for solving it, which is usually picking out which, what are we going to use, the Sakatoa, or are we going to use the sine law, the cosine law, Pythagorean theorem, some of the interior angles. I mean, there's a lot of things we can use, and no one's really going to see you're using the wrong one if you're getting the right answers, right? And that's sort of key to this whole thing. Okay, so that's how we went through this. And yeah, so the diagram is really important. It's worth at least a mark, even if everything else falls off the rails. So make sure you you put a diagram down, and it helps me to sort of see what your thinking was. Okay, so I think we're just going to leave it there. It's a little short class, but honestly, the lesson 15 was a pretty short lesson. So tomorrow we'll be back live. Bring your unit 4. We're going to start unit 4, and yeah, that's it. So thanks for joining us today, and we'll see you live tomorrow. Bye now.